Okay, we can begin, I believe. So, welcome everybody to the third annual Rushton Academic Excellence Lecture. Now, this is a series that is in honor of everything that Professor Gerald Rushton has done for Gerard. That's embarrassing. After like 20 years or whatever, I messed up your name in public. Oh well. So I'll get one faux pas out of the way, and then maybe I'll be okay for the remainder. So Jerry is, as you all know, he has been an icon in medical geography, in spatial analysis and location theory. And this is kind of our way to remember that every year, to kind of bring him back on campus, although he's back doing interesting and important stuff all the time, and to bring someone of note to the campus and talk about their research and their ideas in these general areas that Jerry has contributed so much to over the years. And I think, frankly, this year we really kind of did ourselves, bringing Professor Luc Anselin here to campus to talk to you today. So he got his PhD and master's in regional science in Cornell University. He got a master's and bachelor's degree from the Free University of Brussels. He is currently I'll probably mess this name up too as well, the Steinfreiler Distinguished Service Professor of Sociology at the University of Chicago, and the first director of a brand new interesting center for spatial data science. And that's really pretty exciting and pretty innovative, and we're kind of enjoying learning more about that as Professor Anselin is around talking to us. Before that, he was the Regents Professor in the School of Geographical Sciences, Urban Planning at Arizona State University. Before that, he was the Excellence Professor at the University of Urbana-Champaign in the Department of Agricultural and Consumer Economics. Before that, University of Texas, Dallas. Before that, UC Santa Barbara. Before that, Ohio State University. And as I was going back through this list, I found it kind of interesting because there's this periodicity in those. And then if you think maybe short term, maybe kind of a small end problem, if you think about his last few assignments, there's kind of a spatial trend to it. There's kind of there's a trend in kind of the prestige and importance, not only of the institution, but of his role that he plays within those institutions. So I found this really kind of fascinating. So I took this spatial and temporal and attribute data and I plugged it into GeoDa. It turns out there's like an 85% probability that in 2023, will be the dean of the first College of Spatial Science at Princeton. That's about all that's really left, and it's really impressive long trajectory of his accomplishments so far. He is a member of the National Academy of Science. He's a member of AAAS. He's won prestigious awards from the Regional Science Association. He's well known for his GeoDa software, and I think probably the favorite of students everywhere who can just use that software and not have to think about all those messy equations, right? Just kind of go in there and do their stuff. It's my pleasure and my honor to introduce you. Thank you very much for coming to honor Jerry and to enlighten us all.
Thank you very much, Dave. I will push this button and hope for the best. Okay, the title, and then I'll backtrack a second. So it's really not 21. It just sounds better. It's 22. So LISA stands for Local Indicators for Spatial Association, and that will be the topic of my talk. But before I get there, I've known Jerry for a long time, and he might not remember this, but this was my first exposure to Jerry's work. It's this little monograph on optimal location of facilities that I actually bought, and I was going to bring it as a prop. But when you move around a lot, you don't find anything anymore in your office, and I could not find it. But I remember it had a really ugly color. It was either silverish or yellow, and this was before fancy printing, and so it was all exactly, this was the cover. This is what you see on the cover, what you see there. So that was my first exposure to Jerry, and then I got to know him better through the National Center for Geographic Information and Analysis, where he was on the board, and he was also a good friend of my colleague Reg Golich, who gave him an excuse to escape Iowa winters every once in a while and come out to Santa Barbara. And as I was thinking about what I would talk about, I was looking at something else and I ran into this paper that, of course, I had known for a long time. So I decided to talk about ways to detect local clusters in anything, in some variable. So that's what LISA stands for. And first, I was going to just kind of give an overview of the motivation for this local statistic, how I came about doing this, and what some of the extensions are. But as I mentioned to Jerry in a conversation, this actually prompted me to start looking at it a little more closely, and actually for the first time in a long time, I actually did something new. I mean, you might think that I do new stuff all the time, but I don't think of it as that way. But so I looked at one of the family of LISA statistics, the local Geary statistic, and then pushed it a little further. And I was really I discovered that it's almost not used at all. And it's also not really implemented in the usual software packages, open source software packages. So I worked on this a little more. And then I also had been thinking about this problem of combining multivariate clustering and spatially constrained, spatially contiguous clustering, which is a really tricky problem. And so out of that, as it happens, as often is the case, it's actually very straightforward, came a multivariate local Geary statistic. And so I will talk about that a little more, and I will illustrate it with an interesting historical data set of the moral statistics of France in 1833. It's just a nice sample data set, 85 observations, so you can't really break anything in that. And it happens to have been used as an illustration of multivariate clustering with a little bit of space added on. And so I thought it would be a nice kind of example to see how these quote unquote new methods compare to the other way of doing things. And then I can't help it, but if time permits, I will give a little demonstration of GeoDa, the latest GeoDa. As I told somebody, I have 5 different versions on my laptop, so if one crashes, I'll use another one. But this is hot off the press. This is the binary from last night that we're constantly developing. So, but I wanted to show it to you to see which direction we're going in and some of the new features of the software. But you know, I can keep that short or spend some more time depending on how things work. So a lot of this work has been over the years funded by NSF, most recently through a CyberGIS grant, of which your illustrious graduate, Shaowen Wang, was the PI, and also by AHRQ. So LISA, what does it stand for, and what is the idea behind it? So it's a local indicator for spatial association, and I say spatial association on purpose because autocorrelation has a direct meaning as a correlation coefficient, which is a product moment statistic. And in fact, as we'll see, the local Geary is not a product moment statistic, but is a square difference statistic, so it's a little bit different. And so there's 2 main ideas that I laid out in this paper in '95, is that it's a local statistic, so there's one for each location. So it allows you to identify clusters, hotspots, cold spots, and so on. And then the second aspect is a little bit more technical and maybe not necessarily directly of practical interest, but there is a connection between a global spatial autocorrelation statistic and these local statistics. So in other words, the sum of the LISAs is in some sense proportional to a matching global statistic. So just a little bit of bragging. This article happens to be the most cited article in geographical analysis. And, you know, Morton O'Kelly keeps reminding me of that every time I see him. And so that's a good thing, right? What it shows is that this idea of clustering actually has appeal in a wide range of disciplines. And these statistics, and the local Moran statistic in particular, has been applied literally in fields from A to Z, from archaeology to zoology, not always appropriately. And I'm afraid part of that is a consequence. Maybe it's my own fault. It's so easy to do in GeoDa. You can just click, 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 and you get these maps, and not everybody necessarily interprets them in the right way, unfortunately, but that's just part of the course. So what we want to do with these local autocorrelation statistics is be able to assess significance. So this is where, as I'll elaborate in a few minutes, we get on a slippery slope, because it's really not that easy to assess significance in a formal sense. But at least it's better than just simply having a map. And once we have this significance, we can use this to identify spatial clusters, hotspots and cold spots, in the sense of locations, observations where the values for a particular variable, an attribute, are more similar to their neighbors than they would be randomly, or more dissimilar. Those I call spatial outliers. And so spatial clusters are really about positive spatial autocorrelation. Spatial outliers are about, if you wish, negative spatial autocorrelation, or actually more heterogeneity, breaks in the landscape, if you wish. Something is an island, a high crime area surrounded by low crime areas, low income areas surrounded by high crime areas, and those kinds of situations. So one of the issues, methodological issues, and I'll come back to that in a few minutes, is that you can look at this in the absence of global spatial autocorrelation. In fact, some of the early applications were in situations where, say, a global Moran's eye statistic was not significant, but nevertheless, so on a global level, there was no indication of spatial autocorrelation, but nevertheless, if you focus on localized scale, a more localized scale, there is. So the more common situation is when you have both global autocorrelation and local, and that has implications for what is the formal value of your significance, which is, as I mentioned already, a challenge. So what is a Lisa statistic? It's actually very simple. Whenever you can write a global statistic as a sum over the observations, so you sum over I of something, I call it just a component, subscripted by I specific magnitudes. It could include the neighbors. Then the local statistic is this component, and the global statistic is simply added up and rescaled as appropriate. And as it turns out, a lot of the spatial autocorrelation statistics are actually double sums. They're double sums of magnitudes measured at each location, and you sum over I, which is the locations, and then within that you sum over J, which is the neighbors. So for each location, if you just sum over J, you have a local statistic for that location. So that's the general idea. And the most commonly used one is the Moran's eye statistics, most likely because Moran's eye as such is probably the most used global spatial autocorrelation statistic. And it's actually very simple. If you look at the bottom line, the statistic is some scaling factor, which is basically related to the variance of the process, but that's the same no matter where you are in the process, so you can as well ignore it. And then the rest is a simple cross product of the value at a location, and if you wish, the average of the values at the neighboring locations. So that's all it is. So it's very easy to compute. The challenge, of course, is how do you know whether this is significant or not, which is a little bit more complicated. So first, the link between global and local. That's very easy in the case of Moran's eye. Simple algebra shows you that the global Moran's eye can be seen as an average of the local value. So why does this matter? Why is this relevant? Well, behind the scenes and under all this spatial a lot of the spatial analysis are some assumptions of equilibrium, some assumptions of spatial stationarity. And we're always looking for indications that these assumptions might not be satisfied. So comparing the global moran to its contributing factors is one way in which you can look for evidence that maybe this is all driven by one or two observations, but then in the rest of the system there are different patterns. So where I'm always looking for potential breaks in the system, which I call spatial heterogeneity, and this is one way of informally, admittedly informally, looking at the stability in the system as a whole. So what you really want is that most of the individual local statistics kind of average are close to the overall average. What you don't want is that a bunch of them are really very large and others are very small or negligible. And so that suggests some structural break in the system. So inference, coming back to inference, is really a challenge. And one can do an analytical derivation. In the original paper there was one, and that can then be approximated by a normal distribution, but the approximation is very poor. And the reason, intuitively, not formally, intuitively, the reason the approximation doesn't work that well is because it is a local statistic, and it only takes a few observations into account. And for these statistical approximations to work really well, you need something similar to a law of large numbers. So you need more information to get the averaging that you need to get to some stable distribution. And in these local statistics that sometimes only take 2 or 3 observations into account, you're just nowhere near this kind of averaging that you need to get the analytical property. So I say over and over again, do not use. Right? If I had whiteout, I would take it out of the original paper, but it's there. Unfortunately, and this is where maybe we cut off the camera, some not to be named software does use the analytical results to report significance of local moran size. The preferred approach is a data-driven approach. It's a computational approach. It uses something that I call conditional permutation. And conditional permutation is just a special case of general permutation, which is used in many situations in spatial analysis to reflect the null hypothesis of spatial randomness. So under spatial randomness, any value can be anywhere. So you take the attributes you have and you shuffle them around and keep shuffling them around. And that gives you a sense of how whatever it is that you're computing, some statistics, some density measure, whatever it is, you can recompute it for these reshuffled data sets, and that gives you an idea of the behavior of that statistic or function or curve under spatial randomness, and then you can compare what you actually measure to that reference distribution. So that's the general idea. For the local statistic, one complication is that you really can't shuffle everything around. So you have to hold the value that you have at the given location and kind of take that out of the vat, and then all the other values can be shuffled around. And you have to do this for each observation. So this very quickly becomes computationally challenging, but it's also embarrassingly parallel. So it's very easy to scale it up computationally. So that then gives you for each location a reference distribution, and you can decide then whether the statistic is significant or not. And that's where some of the problems speak, and what is the p-value that you use. This is a classic example of multiple comparisons, where you use the same data over and over and over again to get multiple test statistics. So the actual true underlying p-value is not what you think it is. So you have to correct for that. How you correct, I'll revisit in a few minutes, but that's one of the challenges. So my advice is don't take these p-values too seriously and look at it more in an exploratory fashion. I mean, if it's highly, highly significant, there's probably something there. But if you're kind of on the bubble at the magic 0.05, don't get too excited. It could be just a fluke, a spurious thing. So the end result of all this stuff is what GeoDa has been promoting and what I have been pushing is what we call a local cluster map. And this is a map of only those locations that have a significant result for the statistic. This is also where my approach differs from what you might see elsewhere. So there's a lot of empty space there where it's not significant. There's no point even knowing what the statistic is because it's spatially random. Right? And unlike some other statistics that are technically not LISAs, like Geddes-Orr GI and GI star statistics, they're in the same spirit, but they don't have a global counterpart that they are directly proportional to. So in that kind of limited technical sense, they wouldn't be a LISA, but for all practical purposes, it's the same general idea. So in a Geddes-Orr situation, positive is hotspot, negative is cold spot. In the Moran's eye, because it is across an actual product, you can't really do that. And so to aid in the classification, I have this other device that I call a Moran scatter plot, which actually divides up the association into 4 quadrants relative to the mean. So it's centered on the mean, and I call them high, high, low, low. Those would be positive clusters, and then low, high, high, low would be spatial outliers. And in the local cluster map, at least the way it's implemented in GeoDa, you can adjust the p-values at which you want to display this, and so you get a sense for the sensitivity of the results for the p-value. And this is an example. I know maybe many of you are familiar with this. If not, you should be, and join the 200,000 other people who are. So this is an example of a local cluster. So this is the 85 French departments that I'm going to use in my empirical illustration later on. And I just took one of the variables. I'll revisit this in a few minutes. And so what we see here is that out of the 85 locations, I cut out Corsica, which is an island. 57 are not significant, so I don't even report those values. And then we have our 4-color scheme, and this is in GeoDa. This is done under the hood, where I mean the statistic itself doesn't tell you whether it's high, high, or low, low. It's the statistic in combination with where the points are in the Moran scatter plot that gives you the classification that then yields this. So this is all done on the fly in GeoDa. So the red ones are clusters of high values surrounded by other high values. The blue ones are the opposite, low values surrounded by low values. And then the 2 other colors, which I will not characterize because my wife tells me that I do it wrong. So it's the bluish ones are the low high outliers. So those are low values surrounded by high values for the neighbors, more so than would be the case under randomness. It's always with that in mind. And then the reddish, light reddish ones are the other way around. So these are spatial outliers in kind of an exploration exercise. I usually recommend that these locations require closer attention, maybe field work, maybe some qualitative analysis, something that explains why they would be different from everything else. Clusters are a natural interpretation, outliers not so much. And so with outliers, you always have the tension between throwing them out, saying they don't belong, we don't want to know about them, or try to figure out, well, why is it that they are different from the others? Okay, so that's Lisa, local Moran's eye, and there's been a lot of work since the initial paper in '95, and there's 3 dimensions of this that I'd like to spend a few minutes on. So the first one, as I mentioned, is the inference, and early work by Michael Tiefelsdorf derived an exact distribution for the statistic under strict assumptions, normality being one of them, but there's other assumptions there as well. And then Sokol, Bob Sokol, and his collaborators elaborated on the asymptotic approximations. And basically, the bottom line of their paper is don't do it, right? And so, based on formal arguments. So then the second dimension, it's really the second and the third are related, is the multiple comparison problem. So in essence, you keep recomputing a statistic on at least a subset of the same data. So if you have 85 departments, in a classic Bonferroni bound approach would say, okay, if your target p-value is found 0.05, then you should really use 0.05 divided by 85 as your value. So that may be fine for 85 departments, 3,000 counties, 30,000 parcels, forget it, right? Nothing is going to be significant. So it's too tight a constraint, and that's also what the paper by Castro and Singer argued, and they come up with a false discovery rate as an alternative, which is a little kind of in between, say, using naively 0.05 and then using this very strict Bonferroni bound, or there's some other bounds that are all basically too strict. So in other words, we never really know what the real p-value is. That's the bottom line. So my advice in practice is, as I mentioned earlier, if it's on the bubble, don't get too excited. If it's highly significant, probably something's going on there that is worth further investigation. And so related to this interpretation is what happens to these p-values if there are different degrees of global spatial autocorrelation present, because the null is spatial randomness, but if you don't have spatial randomness on a global level, what does that do to these p-values? Are your rejection levels inflated, or are they the other way around? And so Art Geddes and Keith Ort have done some work on this, and Pete Rogerson as well. And then on a more technical level, Roger Bevan looked at the power of these tests. Since I was originally trained as an econometrician, I don't really know what that is, and I don't really care about that. It's very interesting disciplinary traditions between fields. And if you come from the survey world and the testing world, you care a lot about power. You want to know how many observations do I need before I can even say anything meaningful about this data. But, so then some other extensions are moving this to different kind of data. So Moran's eye is originally developed for continuous variables. Barry Boots did some work on categorical data. Jacques Till and his co-workers have extended this to points on networks, where essentially network segments become the observations, and so then the neighbor structure is neighbors of network segments, and it's a direct generalization of the idea of a local Moran statistic, but for values that are on segments in a network structure. And then slightly different take on things is to use the notion of local clusters to design optimal spatial weights. And you may be familiar with the amoeba approach that Art Geddes and Jared Alstead have developed, and it's in an R package, and it's used to kind of endogenously define clusters and weights. And there's all kinds of issues associated with this, but this is one direction in which this work has gone. And then recent extensions to space-time and even income mobility. Serge Ray has a paper on Lima, local indicators of mobility association. So those are kind of extensions of the basic core idea. Now, the interesting thing in this literature is that almost 100% of the discussion is either about the local Moran's eye or the Geddes or GI star statistics. Local Geary, nowhere. Computational issues, close to my heart. The whole issue of conditional permutation calculation. So you have to permute the values, typically at least 999 or 9,999 times for each observation. So this is not just doing your permutations. You have to redo them every time for each location. So you have 20,000 parcels, you have to do 20,000 times, 1,000 permutations. So that's something that very quickly bogs you down if you don't do it cleverly. And I still think that GeoDa is the fastest in doing these permutations. I know that it's much faster than R and a not to be named commercial software. But there's been some work on this and on basically cheating. Cheating in not just parallelization, that's relatively simple, but reusing parts of the permutations rather than redoing them every time. And some of these methods show some promise, but there's also, it's not a clear-cut solution. And Serge and I have done some work on this in the context of the PySal package to see if we could speed this up. And the bottom line is you have to parallelize, and that's, then it becomes a hardware issue. If you have great machine, it's very, very fast. Not so great machine, it takes a little more. And then these tests have been implemented widely in both the open source and the commercial world. And I guess that's why have been a big believer in implementing methods in software that is accessible. And I think part of the adoption, for good or bad, of these techniques has been because they have been available in easy to use software. Switching to Geary, poor Geary, in this whole business, this statistic basically gets very little attention. And I've, honestly, up until, fairly recently, had never really used it except in a classroom setting to illustrate, oh, there is another one, but nobody uses it. Right? So the Geary statistic was published in 1954 as a global statistic, as a counterpart, if you wish, of Moran's I. And it is a very interesting statistic in that, unlike Moran's I, which is very similar to a Pearson correlation coefficient, it has this cross-product structure. Geary deals with square differences. So cross-product is directly in line with similarity. If the result is positive, it's positive autocorrelation. If the result is negative, it's negative autocorrelation. Square differences is the other way around. The smaller the square differences, the more alike you are. And the larger the square differences, the more dissimilar you are. So the Geary C, you have to interpret it kind of in reverse. Small values or negative values, if you center them on the mean, are positive autocorrelation, and large values or positive values are negative spatial autocorrelation. So in that respect, the spirit behind Geary C is very similar to what is done in geostatistics with the semi-variogram, which is a measure of square difference for a variable between different locations. There are two important differences between this, the Geary approach and the semi-variogram. Semi-variogram is done for all pairs of locations, whereas the Geary C is, the global statistic is one number for the whole data set. So semi-variogram is really a function for the data set, but it's not a single number. And then the other thing that the semi-variogram gets, you compute, especially the empirical one, you compute all these square differences for all the pairs of points, and then you display them by sorted distance. So then the sorted distance tells you what shape this functional form might have, and then you use this for spatial prediction in creaking. In Geary C, there's no distance ordering, but the neighbors are pre-specified in the weights matrix. So this Wij term that you see there is the sum over J of the differences between a location and all its neighbors on that attribute. And in practice, of course, we know these matrices are very sparse. And so even though you sum over all J's, you really don't. There's just a handful of them. And then the scaling is with respect to the variance. That's similar, the same between Moran's I and Geary C. So then the local version, again, on the numerator, we have this double sum. So we take out the sum over I part, and what's left is the local Geary statistic. And we can either keep all the scaling factors intact, or we can just drop them. And then we have this very simple form on the left, which is a really simple form. And I didn't realize, because I hadn't looked at this in a while, how simple it was. That is just a weighted sum of square distances. So then there's been some work, the very little work that I found on local Geary C was in the Sokol paper, where the empirical moments were derived under randomization assumption. And very interestingly, if you have row standardized weights and a standardized variable, the mean of Geary C is 2. The local Geary C, whereas the mean of the global Geary C, if you remember this from your classes, is 1. But it's 1 because you divide by 2, right? So you can, this division by 2 is not done in the local statistics, so that's where the mean is a little bit different. But for practical purposes, you can, again, carry out a conditional permutation. So you shuffle things around, recompute the statistic. You can take the empirical mean and then decide whether you're below or above and do a pseudo p-value. So that's all pretty straightforward. So let's backtrack a second and look more closely at what this Geary C is actually doing. So basically, it's a square difference. There's a variable. It's autocorrelation, so it's the same variable, univariate, at 2 locations, I and j. So that's, you can call that and I call that the distance in attribute space. So univariate, that's on a line. So think of a line where you have x at I and x at j located on the x dimension, so not in geographic space. What is the distance between I and j in this attribute dimension? That's xi minus xj squared. I mean, that's a square difference. Right? And then when we add this weight to it, we're basically averaging these distances between a location and its geographic neighbors, okay? Not its attribute neighbors. We take the attribute distance and compute it for the geographic neighbors. And so if this attribute distance is smaller than it would be under randomness, then this location is very similar to its neighbors. That's positive clustering, positive spatial autocorrelation. If this value is very large relative to spatial randomness, then this location is very dissimilar from its neighbors, and we call that negative spatial autocorrelation. So that's when you start, I'm building an argument here to facilitate the transition to multiple variables. So it's basically attribute distance weighted to the geographic neighbors. So that's how the two notions of that are in any spatial clustering and spatial autocorrelation measure, the attribute similarity and the spatial similarity or locational similarity. How do we combine these two? Right? So as I mentioned, if this conditional permutation approach gives us a value that's significant and less than the mean, then it's similarity. It's larger than the mean, it's dissimilarity. So, but we don't have the Moran scatter plot. I mean, we do have it, but it's a different concept of similarity. The Moran scatter plot is about cross-product similarities, like a Pearson correlation coefficient. This is a square difference. So sometimes they will match, but sometimes they won't, right? So we no longer have our clear-cut high, high, low, low business. We can use the Moran scatter plot to see where a location is relative to the average of its neighbors. But that's not the square difference, it's just the average of the neighbors. But if it's close to the average of the neighbors, then we can say this is high, high, and similar for low, low. But then there's other situations that can arise because the Moran scatter plot is really designed for a cross-product similarity, and this is something else. This is square difference. So there's this other category where we don't really know whether it's high or low, or it could be a mixture of the two. And then negative association, there is no distinction between high-low and low-high because the squaring gets rid of it. You don't have a sign, so to speak, right? And so there's only negative spatial autocorrelation. So then the visualization of the local Geary statistic is similar but a little bit different from the local moraine. So it's taking the variable called Inference, which is, it's a very funny data set. It's a little dated, right? So these are out of wedlock births. So they call it illegitimate births. So these are the moral statistic, mind you, in 1833. So it's a little bit different work. So what we have in the cluster map that corresponds to local Geary is, again, the non-significant ones aren't shown. The high are the red ones, and the red ones are actually, I know it's a little hard to see, maybe my pointer will appear, it doesn't. So if you look at the Moran scatter plot, there are a few highlighted points. There are actually 9 of them, and they all happen to be in that quadrant. Right? So those are situations where the difference between the value at a location and the values as added neighbors squared and averaged is very small. Right? So those are the ones where we can say high values are surrounded by high. The orangey ones are low. So these are the ones in the lower, this side, left quadrant. And again, I apologize, it's a little hard to see on the screen. And then we have the other categories, right? So other is positive, there's only one of them. And you see that it's a little point that is very close to the mean. So the value, and this is all centered on the mean. So the value of that variable, the Inference variable, is very close to the mean, and its neighbor is also very close to it. So this is the other. They're very similar, but they don't quite fit into the category. And then finally, the negative one are, some of them are in the negative quadrant, as they should be, but one of them is not. So this is just large differences, and you see, I mean, you can think about it as being kind of one dimension is close to the center point, the other dimension is not. So in a cross product that is, you know, you're going to the diagonal, but in a square difference, you exaggerate these differences, so that then pops up. So that's the output of a local Geary statistic, univariate. So now we move to the multivariate setup, and we're using the same rationale. And just to step back, there's been surprisingly little work on this. And it's surprising because in the big data world, machine learning world, it's all about multivariate clustering, unsupervised learning, right? It's just another word for the same thing. And I knew about the Wartenberg approach in 1985 because I put it in SpaceStat at the time. And that approach is basically uses the idea of Moran's eye, but sticks a weights matrix in there to compute spatially weighted, if you wish, principal components, and then uses that in the analysis. There's no inference. It's more of a descriptive tool. And then Dre and co-workers in France, using kind of a French multivariate take. It's a very interesting, different take on multivariate analysis, different from the Anglo-Saxon way. Came up with another way. They call it multi-spati, and it uses spatially lagged variables in a principal components analysis. So it's very similar to the Wartenberg idea, but they take it in a slightly different direction. But both of these are really about global spatial autocorrelation, not local. Right? And then the paper by Lee some time ago looks at a bivariate case and essentially decomposes the Moran's eye into a correlation part, like a Pearson correlation part, and then a spatial correlation part. And then there's some issues with that. There's some fairly strong assumptions that are made for things to cancel out in the equation and to simplify. Okay. So now we're back into Geary and just thinking about first principles, right? So spatial autocorrelation is some kind of a compromise between attribute similarity and locational similarity. So attribute similarity can be thought of as distance in attribute space. So if you think, say, two variables, you have a point, two observations or 2 points in a scatter plot, what is the distance between? That if they're closer, they're more similar. If they're further away, they're more dissimilar. In 3D cube, same thing. If the points cluster in the 3D cube, they are more similar in attribute space. That doesn't mean they're neighbors in geographic space, but they're neighbors in attribute space. So most of the unsupervised learning and clustering focuses on that aspect. What are the neighbors in multivariate attribute space? Some, very large dimensions and all that stuff. But so the concept is perfectly general. Let's take the bivariate case, and we have a distance in 2 dimensions between the attributes. And then we say, okay, what about taking the average for these distances in multi-attribute space between a location and its neighbors? And so that's the same idea as before. We have this sum using the weights applied to these distances. And as it turns out, it's very simple algebra. This is nothing but the sum of the 2 local Geary statistics. So a bivariate Geary statistic is the sum of 2 local univariate statistics. A k-variate local Geary statistic is the sum of k univariate local Geary statistics. Very simple to compute. So it's simply a sum. To keep the scales comparable, I suggest that we divide it by the number of variables, but there's nothing magic to that. It doesn't change significance or anything. It's just an easier way to compare the actual values because they're all, kind of scaled the same. So then, how do we interpret this and how do we carry out inference? Inference is easy, but also complex, as we've seen. So it's easy computationally because it's the same idea. Instead of shuffling individual values around, we shuffle tuples around. So we take for each observation, the set of all the values that occur together, and we shuffle those around in space and we compute the statistic. We, of course, have the multiple comparison problem, but we also have something more because each of the univariate local Gearys is a separate test. And now you're adding these together. So these are not K, if you wish, independent tests. And I don't have a proof of this or not a formal treatment, but out of some experimentation, it turned out that there is an inflation of the p-values with more and more variables. Right? It's kind of like the multiple comparison problem. If you have too many tests, your p-values are actually more like 0.20, not 0.05, right? So what I found useful is that if you divide a target p-value by the number of variables, you end up with something that is workable. But again, major caveat, these are not analytical p-values. These are pseudo p-values at best. Again, in an exploratory way, which is what a lot of machine learning is about anyway. If it's highly significant, it is. If it's on the bubble, don't get too excited. The other thing that is different from the univariate case is that the interpretation in terms of high, high, low, low is not at all straightforward. Because with multiple variables, they can move in different directions and still be very similar. As long as they locate in similar environment in multi-attribute space, they would be similar. So what I found is the multivariate interaction is simply too complicated to give a high, high, low, low. For 2 variables, it may work, and I've tried that, and in some cases it works, but in some cases it doesn't. But in general, it's very different. So what you do have is clusters of similar values, which is actually what we're interested in. What you also have is negative spatial autocorrelation. But in the experiments that I've been running, I find very little evidence of that. So it turns out maybe the test is somehow better geared to finding similar locations than dissimilar locations. And if you think about it for a second, as the number of dimensions increase, the notion of dissimilarity becomes harder and harder, because everything in multiple attributes becomes dissimilar in some sense. It's the curse of dimensionality. You just can't do anything about it. So the end result then is again a multivariate local Geary cluster map. And again, the way to interpret this and to think about this is that it's the location of those places that are similar and less so dissimilar in multivariate attribute space, but they're similar to their geographic neighbors. So it combines multi-attribute distance with neighbors in geography as expressed in a spatial weights matrix. Now, just to put things into perspective, I say geography, but it doesn't have to be geography. Any network structure that defines neighbors will work in this respect. As long as, of course, it's not a multi-attribute similarity network structure, because then you're going around in circles. But if it is a separate notion of neighbors, then you can compute this. And, close points in multivariate space, if you then map them, you find out they're close to each other. So this tension is something that we find in any spatial clustering effort. You have to somehow get around it. And spatially constrained clustering, for example, I'll show you if I get around to it with the GeoDa. You can do k-means in GeoDa. Well, these clusters are not necessarily connected. So then how do you get them to be connected? That's the methodological problem. So the illustration using this Geary data for moral statistics of France, I actually wasn't going to use this, but then I found this a paper by Dre and Jean Barre, who actually analyzed this using their multi-spati approach, which is the extension of the Wartenberg approach. And then I figured I might as well use the same and then compare what we find relative to what they find. So this is an interesting study, actually, because it's one of the first multivariate statistical analyses that also has maps and visualization. So from a historical perspective, it's kind of an interesting data set. And it's also been cleaned and streamlined and is available as an R package. It's called the package Geary. And we took it from R and converted it to a shapefile, and it's available as a GeoDa sample dataset. I should say it will be available shortly at the Spatial U Chicago EDU sample dataset collection, and it will be part of that. And as I mentioned, it was reanalyzed, so I had something to compare it to. These are the 6 variables that were considered in the reanalysis, and the following the original Geary approach, Dre and Jean Barre also kind of flip the variables around. So typically, if you look at crime rates, it's crime over people, right? And they turn it around, it's people over crime, so that high values are always good. Okay. It's still, you'll see, it's a little hard to interpret. So if you have a high crime against person rate, it's actually a good thing, right? Because it's more people per crimes. And so they flip 4 of these variables around. Crimes against property is also people over crime. Literacy is literacy, donations are donations. Then these, out of wedlock births are, they call them infants. And they're also flipped, population over the births. And the suicide births and the suicides are also flipped. So just to give you an idea, these are box maps. These are my favorite way of quickly visualizing a spatial distribution of the data. It's a counterpart of a box plot. So it's essentially a quartile map, but with the outliers highlighted. So the outliers are those observations that are outside the fences of a box map. And many of these maps don't have any outliers, but some of them do. So if you just look at a general impression of these maps, and this was when I looked at this in the beginning, say, how in the world is this going to cluster? Because some of them have their high values in the north, some of them have their high values in the south, some of them have the low values in the middle, some in the east. I mean, it's basically all over the map. So this is the challenge of clustering, right? Find the locations that are similar enough, more than random, in geographic space and in multi-attribute space. So to show you the challenge of this, this is and there's a typo in here. I thought initially that the inference variable was infant mortality. Turns out it's not. So these tables still have that, but it's not that. So first impression when you look at these tables, you know, where's the 0.8s and the 0.7s? There aren't any. Very low correlations between these variables. So it's not like, you know, 3 or 4 of these variables, as is often the case in census data, basically all measure the same thing. They all measure something slightly different, and we saw that in the maps as well. And this is confirmed by principal component analysis, which also shows you the first component only explains 35% of the variance. And keep in mind, this is only 85 observations. So this is not like you're doing some huge marketing study with hundreds of thousands of respondents. You know, this is a pretty small data set. The first 2 components only explain 55%. So there's still 45% left. And so it's not until you get to the 4th component that you have 85% coverage. So again, these variables all measure different things, right? Basically, that's the bottom line. So just to illustrate this, this is a biplot for principal components. It shows you the loadings of the components on the different variables. So if the arrow goes high, that means a very high loading on the second component. If it goes far in the horizontal distance, that's a high loading on the first component. And then the map is the locations of the departments in 2-dimensional principal component space. So this is typically what you get out of a, you know, the standard unsupervised learning approach in machine learning, or whatever you want to call it these days, data mining, data science. So this is the map, but it's a map in multi-attribute space, if anything, right? It's not, if you then map these to the geography, it's very different, as we'll see in a second. So this is a box map of the principal components, of the 2 first principal components. So again, we see these differences where the higher values for one tend to be in the north. There's tend to be more of a north-south split. The second one is a little more complicated. The second one also has outliers, which the first one does not. So again, very different spatial patterns from the that are emphasized even when you do dimension reduction. So we have these 6 dimensions. We looked at the 6 maps, you know, to simplify this. We reduced the dimensions by using the principal components, but still, there isn't really anything that comes out of this very clearly. So then we go back to local Moran and run a local Moran on each of these variables. And again, it's all over the place, basically. And my favorite one is the one on literacy, which actually picks up what in the 1833 piece is called La France éclairée and La France obscure. So La France éclairée is the enlightened French, the smart ones, the ones that read, and then the other ones don't read, right? So the red ones read, the blue ones don't. And I didn't make this up. This actually comes out of this original paper, and the local Moran picks it up. As in my experience, you know, now doing this close to 22 years, it does in many, many instances. So I do this a lot with what we call substance experts. So we run the local moran and out pop these clusters and they say, oh, that's where that is. Oh, that's where that is. You know, and so without knowing anything, that's why it's unsupervised, without knowing anything about the data, these patterns do come up. So does local Geary do the same thing? Well, yes. I mean, look at, again, the literacy map clearly picks out these two patterns, but it's not the same. And why would it be the same? There are two different criteria of similarity. One is a cross product, one is a square difference. These are not picking up the same things. Especially the square differences will emphasize extremes because of the squaring. Right? So this is the result, the same local cluster map as you would have in Moran's I. And you see that they're very similar, but they're not identical. So this is, for example, crimes against persons. And you see that in general, the hot spots, the high spots are picked up, but a little bit slightly different geography. And then the low spots are also picked up with a slightly different geography. So in broad terms, they are picking up similar broad spatial patterns, but at the detail level, there are differences. And I looked at these differences. So if you look at just not looking at correspondence just in general, how many locations are significant for these statistics using the same criterion, it's very similar. And if anything, Geary tends to have a little fewer, but is basically the same thing in terms of overall significance. So that means that, you know, as flawed as this may be, our little ad hoc p-value trick is not being too misleading. It's basically not ending up with everything being significant or nothing being significant. They're very similar in terms of what they pick up overall. And then in terms of overlap, it's about half of the locations are exactly the same in terms of, I mean, the direction is always the same. There's no conflict between positive and negative between the two, but, you know, so there's a core there that is picked up by both statistics of similar locations. And I didn't do this, but if you wanted to, you could do an overlay and actually pick up those locations. And those would be the ones that in an exploratory exercise, you would want to spend some time investigating further. So then I said, well, what about these PCIs? What do they pick up? And they pick up broad patterns. And in fact, this is very in line with the results of Trey and Jean-Bart, who give you these maps of the PCI. They're little square maps with larger and smaller values. And it's very, you know, picking up the same thing. But here, what they describe in words, here we can quantify with the local array. So then the multivariate local Geary, throwing all 6 variables together. You might say, well, why don't you do a simple overlay of your univariate local statistics? There is not a single location that is significant for each of the 6 variables in one of these local Moran or local Geary maps. Not one. For 5 variables, there is 1 location. 4, there are like 4 or 5, and then it goes up. So the correspondence is mostly in the very low dimensions. And these are not the same variables. So when I say they match for 2 variables, these are not necessarily the 2 variables, you know, for all the locations. But that's the lack of overlap. So again, it emphasizes how these 6 variables are really capturing different dimensions of the moral statistics in France at the time. So this is the end. Well, no, it's not. I forgot. I have one more. Just comparing the local Geary for the first principal component to the multivariate one. So there are some similarities. So the first principal component is picking up something of the variability among the 6 variables. But as we saw, it's only 35%. So there's a lot of other information that is embedded in the multivariate Geary. And I don't know how long I'm supposed to go, but let me just give a quick GeoDa.
Till
Yeah. I go till 5.
yeah, if you'd like to.
Okay. Well, don't tempt me. So this is the latest development GeoDa. And I don't know who's familiar with GeoDa, but you might not have seen this version. So we made a lot of improvements under the hood. One of them is that we now have a bit of a history feature. So the latest data sets that you analyze are kept here, and then the sample data from the sample data collection are all available here. So if you wanted to start in a classroom with analyzing Columbus, there's Columbus. You don't have to load it or anything like that. So then let me show you the other feature that maybe is not fully appreciated. We have project files. So project files contain, they're basically XML files, they're text. You can edit them if you know what you're doing. They contain the information on the variables in the data set. Any transformations, for example, if you do space-time analysis in GeoDa that involves a grouping of variables over different time periods, that grouping is recorded in your project file. So next time you don't have to do it again, it's already included. Most importantly, whichever weights files you create are already available for analysis in GeoDa. So you no longer have to each time recreate or load the weights. One of the advantages of this is that there's a little bit of metadata. I mean, metadata for spatial weights are a real problem, and unless you're creative with the file names or things like that, which is my old approach, you basically don't know which is which because it doesn't say, they're just numbers, right? So this actually keeps track in the project file of, for example, whether it's a queen or rope contiguity file, whether it is symmetric, and what is the variable that you use to make the one-to-one match with the data. So let me start by, I can give an overview of GeoDa, but let me just focus on the topic of this talk, and then if we have time, I can show you some other things as well that have been added recently. So we're going to do a basic map. This has the collection of all the possible maps that are available, and here's the box map. Let's take prime persons, and this is exactly what you saw before. So this is one of the descriptions of the data. The Moran scatter plot is here. So that's another measure of spatial autocorrelation. The slope of this line is the magnitude of Moran's I. If you want to carry out inference, you go to randomization, you carry out the permutation, so it gives you a sense of how significant this is, highly significant in this case. So this is the reference distribution I mentioned, and this is the actual statistic that we observed. So this is all pretty standard stuff. What is new in GeoDa is that if you, for example, this is also new, the way we highlight, I actually don't like this, but everybody else does, so it's there. I like the old cross-hatching thing, but this is uses, what is it? Transparency to select the selected variables versus unselected. And in the preferences, you can adjust how dark or how light you want this to be. And the other thing that changed is that now automatically, it used to be to define your brush, you had to push control or some other button, that you don't have to do that anymore. So this is our brush in the map. And as we move the brush, the Moran's I gets recalculated on the fly. And so on the right, on the left, you have the Moran's I calculated for the selected observations. And on the right, you have the statistic for the other observations. Now, way back one, you could do this in GeoDa, but it wasn't right. It wasn't right because it used the weights matrix as it was defined for the full data set. Right? So, Moranzai, you actually don't need the weights matrix. You have the value and then the spatial lag. So if you take a subset, you can recompute the statistic using the value and the spatial lag. But the spatial lag is the one for the original with all the neighbors included. Right? So now we recompute, I mean, this we don't really, but we recompute the weights on the fly. And so as you move the brush over the data points, the weights matrix is adjusted to reflect only those data points that are selected. And it's kind of a moving window, and the statistic is computed for that window. Why would you do this? Again, going back to my earlier comment about spatial stationarity and equilibrium, you don't want to see this line flipping up and down too much, because that suggests that there are subsets in the data that show very different correlation structures from other subsets in the data. So that's a new feature which we released very recently. So then we move over here. These are the local statistics. And this is the classic local Moran statistic. Same approach. We can pick between a significance map, which I never used, the Moran scatter plot, which we already did, and have our cluster map. So this is the cluster map that we saw. I mean, one of the 6 cluster maps is the same. And so the new thing now is that we have here a local Geary cluster map. This isn't out yet. This will be released within a month, I think. So very same interface. Again, the choice between a significance map and a cluster map. And we go, and I picked the wrong one. So this is the cluster map. Again, the same picture that you saw in the slides. And then the multivariate one is same button. We go here and we take our 6 variables and we have. And now since I have internet connection, I want to show you this, which you may be familiar with. So this is a base map of France under, and you can play with the, how dark or how light you want to be this. I always forget, but this is, can be adjusted so you can make the base map stronger or lighter relative. So now, all of a sudden, you can start looking at what do these clusters mean in terms of course, these highways weren't there in 1833. But the cities were there. They were in the same spot. You'd see where Paris is, and you'd see where some of the major cities in the south are, and how these clusters are organized around these cities. And then one feature that we have is that you can change what I call the significance filter. So let's say we turn this to 0.01, and then these are much fewer, of course, but then still showing some areas, some groups of departments that are very similar to their neighbors. So that's the Geary part. And then another aspect in the same context is that we can do principal components analysis. And so we take our 6 variables and we use all the defaults. So this gives you the standard results that you would see in any principal components analysis. And then based on this criterion, the 95% threshold criterion, it says you really need to use 5 principal components. But that kind of defeats the purpose. The whole purpose is to reduce the dimensions. And so if you're going to have to go to 5 components, you might as well stick with your original 6 variables. So, but just to show you what this does, let's say, well, actually, I shouldn't do this because I already have it. But you can save these as new variables, and they're added to the data table. And I'm not going to do this because they are already in the data table. So I've done this before, so they're in. So you save them to the data table. And then, of course, immediately they are available for mapping. And you have a map of the principal components. So that's another way of getting at the multivariate analysis, but through the classic non-spatial approach using the principal components. Another new addition is k-means clustering. So k-means clustering is non-spatial clustering. We take the same 6 variables, and now we have to specify the number of clusters. So let's say 4, and we just, we're gonna save the clusters in a variable. And once you run this, it gives you the map of the clusters. And this is the, you know, the usual problem, right? So you have these clusters and they sort of hang together, but not fully, right? So the challenge for spatially constrained clustering is to start reshuffling these so that you end up with nice, compact and contiguous blocks that are still more similar inside and dissimilar between, and maximize that criterion. So it becomes an optimization problem. And this is also to illustrate that this, I mean, this is only 85 observations. If you do this for the US counties, it gets much messier and it's really hard. I mean, you do get big regional trends that we all know, you know, the Midwest, the South, the West, New England, these things tend to come out. But then there's all these other pieces that don't really fit. And so what do? I mean, you want 4 clusters and you end up, I mean, you could call each of these a separate cluster, which is what some literature suggests. So instead of 4, we have whatever it is, 9, and call those the clusters. But, or we can start merging them and shuffling them around in some organized way. So we have k-means, and we also have added very recently hierarchical clustering, where we still need some, there's some missing pieces, but basically it works. Let's take 4 again, and as you know, let's do complete linkage. And you know, this is the typical hierarchical clustering disaster where, you know, a lot of things end up in the same cluster, and then it's much harder to, you know, I mean, depending on what you do. For example, if I take a different criterion, you know, this is great for classroom, and this is always my hidden and not so hidden agenda. So if you take single, you get that. And so you can illustrate, depending on the different criteria that you use to do the clustering, that these resulting maps. I mean, the trees, that's the missing part. Usually you show the tree, the dendrogram, and you can see where you cut. But we don't have that yet, but we have the map. And so you see geographically, you know, where it ends up. And so that is our venture into multivariate analysis from an exploratory perspective. And we're working on, you know, obviously refining this, making sure it's stable and it doesn't crash all the time. It didn't crash. So, and then, of course, the counterpart to this is the spatial regression. And the next big release of GeoDa will be 2.0. And 2.0 will have spatially constrained clustering in it, and all the spatial regression functionality that is now in GeoDa space. So GeoDa space is really a graphical user interface on top of our Python code from the PySal library, SPREC, the spatial regression code. So all that stuff will migrate into GeoDa. We might have to call it GeoDa Pro because it becomes much bigger. because basically we're wrapping around the Python code without changing a single line of code. We just have a C++ wrapper around it, so that all that functionality then becomes available through one interface. And since I want to have some questions too, but the bigger picture is that, since somebody asked me about that this morning, we are moving to a cloud-based system. It's called GeoDa Web. This is an outgrowth of our CyberGIS project, and GeoDa Web will be a graphical, is designed to be a user-friendly, browser-based graphical interface to spatial analytical functionality. Not just ours. I mean, we have a lot of it in here and in our PySal library, but also R and whatever else we can find that is useful. So basically, we become, if you wish, the middleware, where we take the functionality, we're the curator, we do the quality control, and then we make it available through a browser for, you know, any kind of analysis. So then we can very quickly scale up to include point pattern analysis, which we've never done, but there's some excellent packages in R for point pattern analysis, or to do geostatistics, which also we've never done, but again, we can leverage the code in R and provide it in a user-friendly framework. And this is where we have a little bit of a, you know, or I have a little bit of a kind of a different take on spatial analysis. I think there is a part of the R community that wants you to suffer, and you're really gonna work very hard and understand the code before you're going to do anything. And if you're not willing to go that route, then you shouldn't be doing it, period. Now, I tend to be a little bit on the other side and maybe make it too easy for people to do, so that they do stupid things, and they do, and that happens as well. So this tension is basically unavoidable, but I see that the R world now with Shiny is moving a little more towards a little more user friendliness as well, and a point and click, which, you know, even 5 years ago, if you had mentioned that at an R as a user meeting, they would laugh you out of the room. So, I mean, it's the reality. I find it, there are certain things you need to program and you need to use the command line for, inevitably, but there's other things, especially I find in a teaching environment where you basically can't beat the graphical user interface. And in part, this is selfish because I cannot remember these commands, but in a GUI, I always remember what I have to do. So that's where I'd like to close and just give you a chance to ask me some questions or not, and then we'll talk at the reception, which I presume is following.
If you have to leave before the reception starts at about 5:15 at the Share, which is in the Sheraton restaurant, so hors d'oeuvres, and the university won't let us buy you alcohol, but food will be there. So join us, please. Now you can ask your question.
Okay, so my question was, I guess I'd be interested in hearing a little more how you decide which statistic to use, either the Geary's or the Moran side. I'm sure they both have their benefits, but I'm just not 100% clear.
Yeah, it's not a choice. It's a both. I think what I discovered, and I was, you know, in a sense, a little bit surprised, is that these two, I actually knew this from the global statistic, but on a local level, it's actually more interesting. These two approaches pick up different patterns in the data, different measures of similarity. So they each contribute something. And remember, this is an exploratory exercise, right? You start by knowing very little. You have a lot of data typically, and you try to find patterns in the data that then hopefully will help you to formulate hypotheses, which you can then express more formally in maybe some model, some process model that you can then test with the data. So that's how I think about this. So in that respect, the more the better, right?
So use both.
I would use whatever you have. I even these non-spatial ones, they tell you something, because they tell you something about the tension between the multivariate similarity and the spatial similarity. And so some of these are k-means, maps, are very nice, and they just kind of group things nicely, almost like spatial clusters. Some are not. I mean, I don't have an example here, but in some of the you know, trying this out with data for Chicago, some of these k-means maps, they're all over the place. You know, there's no grouping whatsoever. So in those situations, you actually have a challenge, because the spatial autocorrelation makes a compromise between the attribute similarity and the spatial similarity. So the k-means is attribute similarity only. Right? So the moment you bring the spatial consideration in there, you're going to lose something in this attribute similarity. So is that meaningful enough for you to then move forward with pattern? It's basically pattern recognition. So, and some, I know some part of the profession would argue that the spatial part is irrelevant, and I run into that, I wouldn't say on a daily basis, but regularly where I am now. And so it's a constant argument to make, and I've been making it for a long time, that space does matter, and that there are insights to be gained by using these methods that are spatially explicit. And so I think the short answer to your question is use both.
Thank you.
You mentioned spatial randomness several times. I was wondering if you have a position on trying to do better than spatial randomness. If you have a priori some knowledge about what the structure should be, rather than looking at departures and sort of preload things and test things against that.
Yeah, that's an interesting argument and an interesting discussion that's ongoing. I read between the lines that basically spatial randomness is not very interesting, and it isn't. And the purest way to look at this is that the spatial randomness is the null hypothesis. And basically you want to reject the null hypothesis. But the alternative hypothesis is really only a tool to help you reject the null. You're not really accepting the alternative. And so if you take something other than randomness, a priori I don't have a problem with that, but the reason for it has to be very strong. And I think, personally, I think the only way to do it properly is in a Bayesian framework, where you actually assign uncertainty to these priors, where you say, well, I think this prior structure may be there, and how is what I find actually confirming that or departing from that. So as far as I understand it, the literature on Bayesian clustering does some of that. You know, doesn't necessarily take spatial randomness as the point of departure. So I don't have a strong feeling against it. I find that it's easier in an exploration phase to start with the null, and maybe later say, well, there is a strong, for example, east-west pattern, right? And how different are we now from the east-west pattern? But then my personal preference is to move into more of a regression framework, or more of an analysis of variance framework, a little more formal, or if you wish, a fully Bayesian framework.
Are we done?
I'll ask one more. Do you haven't mentioned this, but do you use in any of the packages, and maybe in some of the regression packages, Moran eigenvectors, or also called principal coordinate neighbor matrices?
Yeah, I don't.
You don't.
How should I put this without offending anybody? I'm moving into a big data world. And in a big data world, you can't compute eigenvalues. So that's one answer. That's a practical answer. So, you know, you can't compute eigenvalues for 10,000 observations. I mean, you can approximate, but then you know. The other, more fundamental response is that there isn't really a, or at least in my view, I should even say in my opinion, there isn't a solid data generating process for the eigenvalues as such. So it is an interesting decomposition of the weights. And I think in that respect, even in the earlier literature, this goes way back. You know, some of the Ohio State folks were looking at this as, you know, kind of a signature of a map, right? And looking at the principal components. But and maybe it's my, you know, even though it's very far back, my economist training, I cannot buy this as a viable data generating process. In addition, it does not lend itself to, you know, statistical thinking like asymptotics, because the eigenvalues change with every weights matrix. So it's very difficult. It's fine, I think, as a kind of a quick summary, but in terms of a solution to correcting for autocorrelation, I simply don't buy it. There is no formal, I mean, I hate to use the word proof because that's maybe too strong, but there is no formal showing that this, in fact, is the case other than on an ad hoc basis. This probably should be edited out.
Okay, thank you once again. Everybody to the share.
So the share is actually a real thing.
I don't. It's like this morning, it was chilly. Now it's like summertime.
Guess
Oh,
what?
if you-